In this video, we present Primula, a tool for probabilistic modeling and reasoning based on the symbolic relational Bayesian network language. Primula can be used for a wide range of reasoning and learning tasks. It operates directly on graph structure data and provides a powerful framework for modeling uncertainty in systems, like people in social network, a sub-basin in a watershed, components in a biological system, and so on. Primula supports exact inference via external tools like SEM-IM and ACE, and approximate inference using built-in Gibbs sampling and map. It includes parameter learning through gradient-based optimization with ADAM and LBFGS, and compiling model into likelihood graphs for automatic computation of likelihoods and gradients. Primula also supports neurosymbolic integration, allowing PyTorch GNNs to be embedded within RBNs. Next, we will show some example of how Primula can be used. In the first example, we present a Mendelian inheritance model. This is what the relational Bayesian network model looks like. The model represents the probabilistic dependencies involved in a simple genetic inheritance example. To visualize the underlying structure, we use Bavaria, which is the Primula built-in tool for visualize and construct relational structures. Here, the relational structure represents a family pedigree consisting of 7 individuals. To perform inference, we export the relational model from Primula to SEM-IM, which construct the corresponding Bayesian network. This allows us to explore how evidence propagates through the network. For example, by setting the evidence on Mike's genotype, we can observe how the conditional distribution over Katie's genotype changes accordingly. This example shows community detection with Primula using the classic Karate Club network. Each node has 2 numeric attributes, C1 and C2, representing soft membership in 2 latent communities. We can use the Learn module and select the relation parameters that we want to learn. We can press the Learn button and wait until the learning procedure stops. Once the learning is done, we can set the result and visualize them in Bavaria, where the color saturation on each node reflects the membership strength in each community. In this small example, we demonstrate how Primula integrates a graph neural network implemented with PyTorch geometric into a relational Bayesian network to model a water pollution in a watershed system. The GNN used here is a 2-layer heterogeneous model trained on a graph with more than 700 nodes to predict pollution level based on the type of crops grown on the adjacent agricultural land unit. Here we can see how the RBN model integrates the GNN and the configuration file for the PyTorch model within the model definition. We can see the tiny relational structure used for this example in Bavaria. In this example, the nodes modeled within the GNN are shown in blue, while the adjacent agricultural land units are shown in green. We can now also perform some map inference for a decision task support. For example, by providing the evidence that all sub-basin nodes have low pollution, we can query now all the land use for finding the most probable explanation on the land use configuration given the observation. In this scenario, the model identifies pasture as the most likely crop type across all the agriculture units.